All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing okay today. I hope that you are enjoying the weather as it's slowly warming up. I think it's supposed to go to like -9 today, so I'm pretty happy about that. You know, I'm from Winnipeg. I was born in Winnipeg, so I kind of like lived in this cold my whole life, and yet I still hate it like a lot. And I look forward to it being over every single year. I like to ride my bike a lot. I often commute to work from where I live on my bike, but I don't do that in the wintertime, and driving and taking the bus is just agonizing and painful, and I hate it. So, yeah. Now that we're talking about stuff that we hate, let's talk about operating systems. Okay, as before, by the end of today's lecture, what I am hoping for you to be able to do is I want us to be able to continue to describe the at a high level the responsibilities that an operating system has. We looked at this last time from the perspective of, here's some code that I've written. What are we asking that operating system to do, and what kinds of things does it need to do to keep what kinds of things does it need to keep track of in order for us to be able to get it to do that thing that we want it to do? We're going to take a look at a diagram today that shows some of the high-level responsibilities of an operating system. And I want to mark up this diagram just a little bit to get a sense of, like, these are the core parts of an operating system, but how have we been interacting with that operating system so far? So going through like Comp 1010, 1020, 2160, and then getting to here, how are we interacting with the operating system? And that's going to inform some of the responsibilities that an operating system might have. The other things that we're going to be doing today is spending some time taking a look at review. So like I said, in the course syllabus, there's kind of a list of the detailed prerequisites that you should have coming into this course. In the course syllabus, I've annotated those with the courses that you should have seen those things in, but today I want to spend a little bit of time just doing some review to make sure that we're all on approximately the same page in terms of what you should be able to do before you're coming into this course. So I want you to be able to list and describe some data structures from previous courses. So I'm thinking about like 1020, 2140. These are the courses that I'm thinking about for this. I want you to be able to apply concepts like design by contract, automated testing, memory management, and debugging. So this is pretty specifically from Comp 2160, where we were looking at this. In this specific thing, the way that I want to look at this is I'm going to do a kind of a longhand written demo of, like, let's build a linked list structure in class today. Just again, dust the cobwebs off of C programming, dust the cobwebs off of using the command line. Remember what things like preconditions and postconditions and invariants are, and how to decide what we should be thinking about in terms of that. For this one specifically, I have posted what I am starting with on the course webpage. So if you want to follow along with what I'm doing with this today, please download that to your system and have it ready to go. Also related to this, I got an email from our tech staff yesterday I think, that all of the Aviary accounts have been set up again. So you should try logging into Aviary with your machine at some point. You'll have to, if you're doing this off campus, remember that you have to use the VPN. I'll post some instructions up on the course webpage later today to help remind you of what that process looks like. And then who you'll have to get in touch with if you've forgotten your password from when you last used your Aviary accounts. So yeah, I want you to be able to do that. The other thing I want you to be able to do is, this is review, describe parts of a computer's architecture. So this is coming from Comp 2280. And this is kind of especially important for our engineering friends who didn't take Comp 2280. There are computer architecture courses that you would have taken in computer engineering before you got to this point, but we'll review a little bit of what I'm thinking about with this. The last part of the things that are coming from Comp 2280 is decide how high-level programming languages are translated to run on a computer. So how do we take these high-level programming languages like C and Java, and what do they get compiled down into so that our computer can actually run the things that we're asking it to do? So before we get to all of that, the last thing that I asked you to do at the end of last class was to tell me a little bit about what you're hoping to get out of this course. And so what I'd like to do is take a look at some of those. This isn't working the way that I was hoping it would work. That's all right. I will just have to read them aloud to you. So what I got was really good. Thank you for sharing those with me. Here are some of the ones that I picked out. I got a really big stack of things from both sections, so these are some of the ones that I picked out. A couple of them were about concurrency and like multiple things that are happening at the same time. So learn more about concurrency. So we're definitely going to be looking at concurrency a lot, again, from the perspective of like, how do I use threads, but also how does the OS enable this concurrency to happen? See a tie into distributed systems. So I'm just curious, how many of you have taken Comp 3010 already? A number of you, okay. So we're gonna see some similar things to Comp 3010, but there's not a huge amount of overlap between these things. The place where there's a lot of overlap between distributed systems and what we're doing in operating systems is when we get to interprocess communication and how processes start to talk to each other within a single system. So if you remember socket programming from Comp 3010, then you'll be familiar with the ideas that we're looking at with interprocess communication. And then the last part is see how it's used for embedded systems. And this one is actually tied to this other one that I picked out, an in-depth understanding of OS systems for use in small-scale systems, microcontroller systems, kernel-level functionality, driver interaction, things along that like, so I can design my own system and have a better understanding of the systems that I use without using a real-time operating system. If embedded systems are something that you're interested in after this course, then I would really strongly recommend that you take a look at taking real-time systems at the 4000 level in our department. Real-time systems is where you start to do embedded systems programming. You basically get the operating system ripped out from underneath you, and now you just have to work with the hardware that's there, and you have to do everything. So like you've got to start thinking about, how do I take this stuff that I want to happen on this machine, and how do I make sure that it happens within a certain time frame, and having to do things like low level, really low level stuff. If you're interested in that, I would really strongly suggest that you take that. Some of the other things that I saw were learn about the functionality of threads. I want to know how concurrency works. I want to know about parallel computing and threads and stuff. We're not going to talk about parallel computing in this course. There is a parallel programming course at the 4000 level, but again, we'll talk extensively about threads and concurrency in this course and how the operating system works with that. There were lots of other ones that were a little bit more pessimistic to a little bit more optimistic. So I got many that said a passing grade, and then a good understanding of what's expected to be understood, a passing grade. And then they got to be a little more optimistic. I want to pass operating systems because it's a requirement for degree. This one just says passing grades. But then they got more optimistic and they started to be good grade. And then they started to be things like A+. I want to get an A+. So I was happy to see some optimism there. And these are the last ones I'll pick. I will be happy to learn about segmentation faults. I promise. That is one of my favorite parts of this course, is to just go through this wild ride of like, the beginning of where the segmentation fault starts to happen and like what ultimately gets to the point of printing the word segmentation fault onto the screen. I really like that. I want to learn how to code software better using OS knowledge I gained from this course. By show of hands, how many people are planning to become operating system developers after this course is over? Okay, 2 people are going, 3 people are going maybe, yeah, nobody else is. So, I mean, that's super fair. Don't get me wrong. I'm not trying to say you must become OS developers after taking this course, but understanding concurrency issues specifically is important in like every level of software development stuff. So I'm thinking about things like, I want to do web dev, and I'm going to have a database behind my web application. There's a huge amount of concurrency stuff that's going on there, and having a good idea of what concurrency is doing underneath will help us with like building good applications like that. This one also appealed to me directly. P.S. I missed you, Franklin. It's good to see you again. Well, whoever you are, it's good to see you again, too. Thank you for coming back. The last one I'll say here is preparation for 4,000 level courses. I believe that this course will adequately prepare you for 4,000 level courses. Yes. Okay. All right. Okay, so let's take a look at that little program that we wrote in C and continue to think about what are we asking the operating system to do at each of these steps, and what does the OS need to keep track of on our behalf? So I'm going to pop up 1 or 2 directories here. And, oh no, I put it somewhere else. I will go somewhere else. So I will go to and I will edit what.c. Here's that program that we wrote in class last time together, that I wrote and you watched me write. These were the different parts that I annotated here. So I updated this a little bit after class to put some comments at the places where I really wanted us to think about. So the first one here is close to the top right now, and it says open. We're calling this function open, and we're asking the operating system to do something for us. The thing that we're asking our operating system to do is to effectively give us access to a file that's on the file system. We want to be able to make use of this file in some way. We're telling it here, I want to be able to just read this file. I'm never going to ask to write it. The operating system can make decisions about what it's going to do in terms of how it represents that file in the background for us. But we're asking, please give me some ability to tell you about the file that I want to work with. The operating system, one of the things that people brought up here that I was delighted to see was that the operating system needs to keep track of, for the program, this program when it's running, the operating system needs to keep track of where is this program running. I just put what.c in here, and this is going to work. I'm not going to compile this and run it because I guarantee it's going to crash, but this will work when I try to run this code. When I say open this file, if what.c is in the same directory as the program when I'm running it. Our operating system will need to keep track of that. The other stuff that our operating system needs to keep track of beneath this is, well, a whole bunch of information about where the hell is what.c on the disk? Where is it actually located on the physical disk that we've got? Whether that's a hard drive that's got spinning platters in it or the flash chips that are in my system right now, where is that actually located? Where are the bits and bytes for this file? There's other stuff that we didn't think about, but we will see, like our operating system also has to keep track of things like permissions and other kinds of metadata. Do I even have permission to open this file? Can I read it? That's not really exposed here, but it is something the operating system is keeping track of underneath. The next part where I've annotated this is on malloc. I'm going to give us a preview of a couple of weeks down the line here, but malloc is not actually doing anything with the operating system. Malloc is asking the standard library to do something. We'll talk about the standard library in just a second, but malloc is asking effectively for something to give us access to some memory that we can guarantee is not going to be used by something else. So what are we asking the OS to do here? For us, for right now, it's enough to say we're asking the operating system to give us access to this many bytes of memory so that we can use it in the context of this program right now. What does it have to keep track of for us to do this, or for it to do this for us? It's going to know what is not currently allocated, how much space is available for programs to use, and what is not currently allocated to programs, for it to be able to give us this information. Down here on the line where we're calling read, we're asking the OS to actually start reading the file, giving us bytes from the file that we had previously asked it to open. What does it have to keep track of here? Where is it starting to read the file from? When I initially open the file, we're at byte 0. And this is a consistent experience for you for every programming language and course that you've done so far. So when you did sorry, I forget now, did you do file stuff in 1010? I don't think so. 1020 would have been the first time you saw it, I think. Yeah. When you did scanner and when you did buffered input reader in Java, when you called .get lines or read or whatever for the first time, it always starts at the beginning of the file. But then every time you call it again, it gives you the next line. Our operating system is keeping track of, given this specific file descriptor, where am I in that file right now? So when I respond to read, I know which bytes to give back to you at any point in time. There's a structure that the operating system is using underneath that we will talk about on Friday and that we'll talk about next week that's called the open file table. This is a data structure that's behind the scenes that's keeping track of, this is the file, where it resides on disk, and where I am right now in terms of this specific question being asked about it. Seeking is very closely related to that. So this is asking us to move around in the file. I want to move from one place to another without actually doing any of the reading. The last part here is, oops, I forgot to call free, and then I'm exiting. Oops, I forgot to call free is, well, that's kind of not asking the operating system to do anything at all, is it? But what are we asking to do the OS? What are we asking the OS to do when we exit? So when we're leaving the main function here, what are we asking the operating system to do when we finish? Implicitly, we're asking the operating system to clean everything up after we're done. Implicitly, we're asking it to do that for us. Not only was it, oops, I forgot to call free, but it's also actually, oops, I forgot to call close, now that I'm looking at this again. I didn't clean up any of the resources that I had acquired when I started working with this stuff. When this program ends, it's the operating system's responsibility then to go through and just clean up everything afterwards. Did you allocate this memory? Okay, good, it's gone now. Someone else is able to use it. Did you open this file? All right, cool, I'll close it for you so that someone else can have access to it. The operating system has to keep track of these different resources that we've got so that when we exit, when we end our program, it's able to do all of that cleanup stuff. Yeah?
Would it still clean up automatically when you exit if you use like a static memory?
So the question, I'm going to repeat your question just for the stream. Yeah, so the question is, would it still clean up if we had just done static allocation of memory? So you mean to say, for example, if I had declared an array at the file scope level? Yeah, absolutely. We'll talk about processes. Again, I'm sorry to keep saying we're going to talk about this later, but when we talk about processes and address spaces and then ultimately virtual memory, we're going to see that the operating system is keeping track of a lot of the memory that's been allocated to a program, including things like where the code goes when it's running the process in memory. And it will do things like clean up after the process exits to be able to get rid of extra stuff like statically allocated arrays. Yeah, that's a good question, though. Thank you for asking. All right, so that's kind of where we were at here. And the operating system it's definitely doing a lot more than what we're thinking about in the scope of this little program, but this is a good place for us to get started in terms of where we're going to go next. So I want to pop this diagram open here. This diagram is kind of showing some of the structure that we've got at a pretty abstract level for what an operating system looks like and what applications and user space coder programs are doing to interact with the operating system. So I'm going to actually open this up over here. And what I want to do is first take a look at this red circle in the middle. This is the operating system. All the things that are in this little box are the things that the operating system is doing and is responsible for. So we've got here the Linux memory manager. The operating system has some responsibility for managing the memory that's physically attached to the system. There's the virtual file system. The operating system has some responsibility to keep track of the data that's on a disk for persistence. There's the Linux process scheduler, and this is going to be the thing where we've got this idea of concurrency. I've got many different programs that are all running at the same time, and they all have to have access to the same limited number of CPUs. That scheduler is what gets to go next, which one is allowed to actually use the CPU and for how much time. The IPC manager here, IPC stands for inter-process communication. This is how different programs that are running are able to talk to each other. So the operating system is going to have to keep track of that. The I/O interface and the network interface. So this is places where the operating system is having to manage some hardware. In terms of us in this course, we're going to be looking mostly at the stuff that's up here on the top. We're going to be mostly looking at these things. We're explicitly not going to be looking at the network interface in this course. That's something that you would be looking at in Comp 3010 more than here, and then again more in real-time systems when you get there. And then to a limited extent, we're going to be looking at this I/O interface in terms of how does this inform the design of file systems. But this is our operating system, and then what this system call interface here is, for us, for now, right now, the system call interface is a place where I can call functions to ask the operating system to do something for me. So the system call interface right now, in terms of our application code, so our application code here is what.c. This is the program that we wrote. The system calls, that's really, really unreadable, I'm sorry. This is what.c. For what.c, the system calls that we were making so far were things like open and read and lseek. These were the system calls that we were making. So open, read, and lseek. These are functions. That's how we're going to imagine them for now. That's how they look to us from the perspective of writing a program, but these are us directly asking the operating system, hey, please give me a file descriptor. Hey, please read bytes from this file right now. Function calls are going to go through this thing called the GNU-C library on a Linux system, but more generally, the GNU-C library here is just the standard C library that happens to be on your system. On Mac OS, this is going to be different than what you have on Linux, but for us, for Linux, it's going to be the GNU-C library. The function calls that we're talking about here are things like fgetS. fgetS is a function call that we're asking the GNU-C library to do, and it in turn is calling read. It's making a system call on our behalf. The distinction between these right now, it's not important. It's really not important. We're going to focus more on the low-level stuff, so like open, read, and write, and lseek for the functions that we're thinking about. But there is a distinction between what the standard library is doing versus what the system call level things are going to be. All right. This is a high-level description of the responsibilities of an operating system and kind of the structure that we have, but it's not in depth. It's not in detail. This is going to be, well, this is a long-term thing through the rest of the term. But are there any questions before I move on to anything else right now? Yeah.
So did you say open read those functions, are they like system calls directly? They don't go through the library?
That's right. So the open, read, lseek, write, these are system calls that are not going through the standard library. They're going directly to the operating system. So this is us directly asking the Linux kernel, please open this file for me. If I call fopen, that's going through the standard library. The standard library is going to give us a bunch of extra stuff, but it in turn will also call open on our behalf. If I call fgetS, that's kind of the same thing as calling read, except it's going to let me read in a slightly different way than what I'm doing with system call stuff. We'll see later that when we're calling these functions, there's a lot of magic that's actually happening underneath that's not just us calling functions, but for now, they just look like functions. Yeah. Any other questions? Yeah.
So if you're developing something, would it be safer to use a system call or the function call in terms of like, if the operating system gets updated, you're going to have to do more maintaining your code or vice versa, things like that?
So that's a good question. Is it safer? I'm going to try to summarize. Is it safer to rely on the system standard library, or is it safe to rely on the system calls to call them directly in terms of like the operating system gets updated and now maybe I have to change a bunch of stuff.
So like the library gets updated.
Or the library gets updated. So the system call interface that's defined by Linux is mostly something that's called the POSIX standard. POSIX is a standard that's across different operating systems like Mac OS and Linux. And so code that you write that targets the POSIX API, which is what the system calls are ultimately going to be, it's portable across operating systems. And that kind of it also implies that if the operating system gets updated, so when we go from Linux 6.7 to 6.8, that system call interface that we're using from C code's perspective is not going to change. Internally, there's lots of stuff that may change, but the exposed API that we're working with isn't going to change very much. So whether you rely on the standard library or the system call interface is, in terms of like, do I need to update it over time, is not super important. There are platforms that don't have a standard library. So back to the things that we were talking about here with embedded systems. Embedded systems often don't have a standard library. You just have to do, if you have an operating system, you have to do direct system calls as opposed to using a standard library. Yeah. All right. So again, this is high level. This is really high level, and we'll spend a lot of time talking about this throughout the term, but in terms of the major responsibilities of an operating system and where the system lies, it's in this circle in the middle that we've got right here. Okay, so let's do a little bit of review here. Data structures and architecture. Operating systems, there's software. Hey, it's C code all the way down. Operating systems use data structures extensively, and we've already talked a tiny little bit, about one of the structures that an operating system is going to use, and that is in the form of an open file table. Table is a fancy way of saying an array. It's a fancy way of saying an array of stuff. Operating systems use data structures extensively. Operating systems are also designed around computer architectures. So when I have my operating system running on this system right here, this is my laptop, this is an x86 computer architecture. It's designed around this architecture, this computer processor. I see lots of people running Mac OS machines. Mac OS is designed to run around their own Apple Silicon hardware now. Here's my phone. This has got another ARM processor in it that's got Linux running on it, and it is also going to be targeting that specific architecture. Operating systems are designed around computer architectures with kind of this major goal to make sure that we can work with that. So let's do a little quiz here about data structures and architecture. I'll give you about 30 seconds to join up here. The code should stay up there the whole time, so if you haven't been able to join yet, you should be able to join throughout the thing. Okay, so I've got 6 questions here. Let's start going through them. Okay, awesome. Yeah. So stacks and queues are data structures that we're going to see a lot in this course in terms of the data structures that our operating systems are using. A stack, partly literally because we will be looking at how like programs are running and how they've got stacks that are being used as a call stack. Queues are going to be used extensively when we're looking at scheduling and stuff. Queues and stacks, the main difference between them is last in, first out for stack and first in, first out for queues. Here's another question. Okay, awesome. Okay, so what data structure, and I'm being really pedantic here about the distinction between the words data structure and abstract data type. Data structure here is the actual physical structure that we're using to do this thing. The abstract data type is like the idea, the operations that we can apply to this thing without knowing anything about how it's actually implemented underneath. We can implement a stack using either an array or some kind of linked list or other kind of linked structure. So that's good. A list is an abstract data type. A list is not a data structure. We haven't talked about how it's implemented. We've just kind of said there's an order to the things that have been put into this thing that we've got. And we can access items in it at specific locations, but we haven't said anything about how it's actually structured. Hash table, I mean, this is a data structure that we could use. And I mean, I guess you could technically use it to build a stack, but it would be really weird and awkward to use a hash table to build a stack. So maybe I should have technically marked that one correct. Maybe I should have technically marked it correct, but I didn't. Binary search tree would be awfully weird to use to try to build a stack. Okay, here's another question. Okay, cool. So tree is definitely what's in my mind in terms of the best ADT to represent this idea of folders and directory structures. As I'm looking at this, I'm going to look at the set one there and kind of say, okay, maybe we could arguably say that that would be also reasonable in the sense that a file can kind of only go in a folder once. It's either in the folder or it's not in the folder. So we could argue and say that, yes, that's another way to represent this. But a tree is what I'm thinking about here. This barefoot Contessa, I feel like, is chasing me around in different courses. All right, okay, so Ashley's at the top right now, followed by Stimulicious and then Homer. All right. Now we're moving on to computer architecture. All right, okay. So the program counter is, I have fetched this instruction and I've increased the program counter to the next one that I'm going to fetch after I have fetched that current instruction that I'm looking at. This is hyper pedantic, super pedantic, and it's not actually super important. The fact that we focused on those two in the middle that's what's really important to me, but being extremely pedantic is the next instruction and not the current instruction. Okay, all right. Okay, so I'm going to just tell you now the answer is 3. There are 3 instructions that this is going to be compiled down into. Reminding ourselves of what this is doing, it's taking the value that's in I right now and changing it to be 1 more than it was before. This is also often written as I plus equals 1, or I is equal to I plus 1. Okay, so There are 3 instructions. There are 3 instructions. Some of you may not have done LC3, but the instruction set for LC3 is similar to other instruction sets. And please forgive me for the terrible formatting that Mentimeter does with assembly language instructions. We obviously were not their primary thought in terms of like how to organize code on slides. Okay, awesome. Yes. It's 3 instructions. I++ is, I gotta load the current value. So if I'm saying I is equal to I plus 1, I have to load the current value of I into a register to evaluate the right-hand side of the expression. So I have to load I into a register. I have to add 1 to that register, and then I have to store the register back into memory in order to persist the change that I've made to that thing. This particular thing is important when we get to concurrency. I'll remind us of this when we get to concurrency, but for now, we're just going to say that it's good for us to remember this, but it's important when we get to concurrency. All right. Ashley stayed at the top. Congratulations, Ashley. Okay, awesome. All right. So what I would like to do now is I'm going to switch back to my slides here just for a second. We've got about 15 minutes left in class. I'm going to check my watch because apparently this laptop is like 2 minutes behind. We have about 13 minutes left in class. And so what we're going to do is spend some time building a linked list in C. This is review. This is something that you have all done a bunch of times, but again, maybe it's been a while since you did it. And so I want to spend some time taking a look at the tooling around working in C and the kinds of things that we should be thinking about. So I want us to be thinking about design by contract. I want us to be thinking about preconditions and postconditions for functions that we're implementing. I want us to be thinking about invariants on the objects and the data structures that we're building up. I want us to be thinking about build tools like make. I want us to be thinking about automated testing. So how do I write a test suite for the code that I'm writing? And then finally, I want us to be thinking about using LLDB to debug. I am not that old of a person, but I behave like an old person a lot of the time in the sense that I spend almost all of my time in the terminal. And I don't really use VS Code. My main use of VS Code is when I need to copy and paste large chunks of text from one file into another file, but I spend most of my time in the terminal. So what I mean to say by all of this is that I know how to use LLDB pretty well. I don't have any idea how to get it hooked up to VS Code. I'm really sorry, I can't help you with that. I don't know how to do it. If someone knows, please tell us. Please tell me how to do it. But I don't know how to do it. So I'm going to use LLDB to think about this. I posted this up on the course webpage as a zip file. So if you've got it on your system, please feel free to follow along with me as I'm stepping through this. I don't think that we're going to be able to finish this, but the point of the exercise is not to actually finish building a linked list. I trust you all know how to build linked lists at this point. Again, it's just dusting cobwebs off and getting comfortable with C and building stuff like that again. So let's pop over here. What I'm going to do is I've got in lecture 2, this is my own directory structure. I've got the contents of that zip file extracted here. In the README, I'm going to generally be asking you to supply READMEs to me for your assignments. So when you're building up an assignment, I will ask you to please provide a README with some information in it. And I'm going to say that this is a good example of what a README should look like for the kinds of things that I'm asking you to submit. You're more than welcome to copy and paste from this document. You're more than welcome to just copy the structure that I've got. Generally, though, what I'm looking for is I want you to be able to tell the person that's reading this, what are these files in general? You don't have to go into a huge amount of detail, but then also how do you build and run the code that I'm providing? So most of the time this will be, you should run make in this directory, and then you should run this program to have it work. But I want to have that kind of documentation. I'll also note here in the README that I've given permission for you to use these files in any way you want. You're more than welcome to just take the make file that I've got here and use it for your own stuff. I'm very happy for you to do that. I really just want to be able to have this available for us to use for the course. So the other thing that I'm going to point out here is I've got a make file here. Again, you're welcome to use this. You don't necessarily have to have this README to PDF rule. That's something that I put in here for your benefit if you want to have a PDF copy of the README instead of this markdown version. This make file uses some things that you may never have seen before. Notice that I haven't really written the words like Clang and how to compile stuff in my make file. I'm using GNU Make's ability to just know how to compile C programs. And these variables up at the top here are what tell it specifically how to do that. The other thing that you've probably never seen before is this. Fortify source here. There's a link that just above that to tell you a little bit more about it. But this is a good way to help with like bounds checking in C. In 2160, we kind of force you to do bounds checking on your own as a part of the course, really, and trying to emphasize the idea of design by contract, but there are tools to help you with that, and this is a tool that you can use to help you with that. The other thing that I'm going to pop open here is I want to pop open the interface that we're going to build. So here's the interface that we're building. This is a header file in C. Generally, I would expect you to produce a header file that's going to hide implementation details. You can use the structure that I've got here as an example of what that looks like. But we're doing a forward declaration here of our list type. I'm just building an integer list. I'm not building some general purpose list structure. This is just going to have integers in it. I have written some comments above each of these functions. So I want to create a list. I want to get an instance of this list structure. This is my constructor function. I'm also doing things like marking down what it will return and what it assumes about the input that's being provided to it. Destroy list is my destructor function. It's going to state things like the value that you're passing here must not be null, it must be a valid list. So I'm starting to think about what are the preconditions for this function, and then what are the post conditions for this function. This is going to return null on success or the pointer to the list on failure. So it can return exactly two values as a post condition, so I can check to see is it one of these two values that I'm actually going to be returning when I get to the point of returning from this function. The last two functions here are insert front and size. I want to be able to stick something onto the head of the list that I've got, and I just want to ask about the size. This is a terrible list. All we can do is insert things and ask about its size and then destroy it. It's good enough for what we need to do for this class's purpose. So I'm going to open up list.c here, and I've already predefined the two structures that we're going to use. So I have this int node structure. This is not exposed to the person or to the code that's going to be using this. I don't want them to know about my node structure. But I do also then have to define the int list as an actual definition of a structure as opposed to just the type def that we have in the header file. So the first thing I'm going to do here is I'm going to write an invariant first, I think. I think that when I was learning this stuff a long time ago, I remember that invariant was the one thing that was hard for me to grok. And so I'm going to start with that. So I'm going to write an invariant for my list structure. I'm not going to write an invariant for my node structure because there's only two properties and there's not actually much there to validate. In most cases, it's null or it's not null, and that's all I can really check about the node structure. But the list structure does have properties that I can assess and decide whether or not this is a valid thing or not. I'm going to mark my invariant here as a static function. I want it to be private to this file. I don't want anyone else to be calling this function outside of this one, so I'll mark it as static. I don't want to return anything, and I'm going to call it validate list. What I want to take as input is a reference to an int list. I'm using const here to basically say that this function will not make changes to the list structure. I don't want to make changes in validation, so I'm going to explicitly say I don't want to make changes in validation. This stops me from making changes to it at compile time, and it's part of the contract to the caller that says, I'm not going to change this thing if you pass a list to me. The first thing that I want to assert is that a valid list is never null. And this is going to help me so that I don't have to put assert not null at every function call. I can just put it here and have this be the precondition for all of those functions. So I'm going to say assert that list does not equal null. And then what I want to do is I'm going to go through, and the structure that I've got for my list is that I've got nodes and I've got a count. I've got a linked list of nodes and I've got a count. So for a list to be valid, the number of nodes I can reach from the head by traversing the list should be equal to count. So I should be able to start at head and then just count every node that I've seen, and then know that assert at the end that count is equal to the number of nodes that I've actually seen. So I'm going to start doing that. I'm going to say int count is equal to 0, and then int node pointer current is equal to list head. I'm not using conditional statements in this function because this function is only going to get called effectively when I'm doing preconditions and postconditions. So if I'm turning that off, I don't really have to worry too much about this. I'm going to say while current is not equal to null. I'll say count plus plus, and then current is equal to current next. And then I want to assert finally that count is equal to list arrow count. So the number of nodes that I've been able to reach from the head node should be equal to the number of nodes that are currently in this list. So my invariant here for my list structure right now is pretty small. There's not a lot going on in this because I don't really have a lot of properties that I can say this is a requirement to be a valid list. So there's not much for me to have here. I'm going to write this out, and then what I'm going to do is I'm going to open another terminal here in the same window, and I'm going to make it. My make file has a bunch of extra arguments in here that are preventing me from doing certain things. Like I've got this function that's not being used, and so I shouldn't have it in the first place. That's true, I shouldn't have a function that I never call in the first place. So I'm going to call this function. I'm going to do that by starting to write the constructor function for this. So create list. This doesn't take any arguments as input because to create a list, in this case, I just want you to make it for me. I don't need to know anything about what you want. I just want to have a list to work with. So to make a list, what I'm going to do is I'm going to call malloc. Int list pointer list is equal to malloc size of list, int list. In the olden days, you used to have to cast the output of malloc to the type that you wanted it to be, but we don't have to do that anymore. Malloc knows enough about what you're asking it to do to auto convert it. There are some places where you may need to do this, like in embedded systems, but for what we're doing with the C compiler that we're using, we don't have to worry about casting it. I do want to do some defensive programming here, so if list is not equal to null, remember that null will return, malloc will return null if it's unable to allocate any memory for you. This is something that we should check for. We could put an assertion here that malloc has not returned null, so doing a post condition for malloc itself, but that's not valuable to me right now, so I'm not going to do that. If list is not equal to null is good enough, this conditional statement, then I'm going to say list head is equal to null, and I'm going to say list count is equal to 0. I don't necessarily have to do this, but you should do it anyway, malloc on some systems will initialize the memory that you get back from it to 0, but this is not universally true. Not all systems will do this. And so explicitly saying, after I've done malloc, these are the default values, is a good way to make sure that regardless of whether you're on a system that's doing this default initialization to 0 or not, you're getting the values you're expecting in here. The last thing I want to do is, if I've been able to create a list, I want to validate my list. So I'm going to call this as a post condition. If I've been able to successfully allocate memory for a list, I don't want to validate a list that's just null because the assertion will immediately fail. That's reasonable for me to return null if it was not a valid list. So I'll return list at the end of this. And at this point, I am taking your time, and I don't want to take any more of your time. We may spend a little bit more time doing this on Friday, but I'm hoping already at this point that some of our cobwebs have been dusted off. I would like to step into LLDB just a tiny bit so that we can remember how to do that, but this is where I'm going to leave it for now. So at this point, you should be able to describe the high-level responsibilities of an operating system. We've now seen this a couple times, so you should have some sense of the high-level responsibilities an operating system might have. You should be able to list and describe some of the data structures from previous courses, so lists and sets and tables and that sort of thing. You should be able to apply concepts like design by contract, automated testing, memory management, and debug you will have done in the past. You should be able to describe parts of a computer's architecture, and you should be able to decide how a high-level programming language is translated down to run on a computer. So taking I++ and converting this down to instructions in terms of what we're actually getting out of this. That's it for now. Thank you for coming out, and I will see you all on Friday. Bye, everyone.